Directional type inference for ML.
Test. Hello, I'm Alistair. I work on type inference for OCaml, and today I will be presenting omnidirectional type inference. This is joint work with Didier, Rémy, and Gabriel Scherer. So before we get into what omnidirectional type inference is, I first want to start with our ideology for type inference for OCaml. So we believe that type inference should be scalable. There are many complex features in OCaml, such as let generalization, static overloading, GADTs, first-class polymorphism, rows, etc. And so we need a type inference approach that scales to all of these features. Secondly, reasonable and meaningful annotations are acceptable for our type inference algorithms. That is, that we do not seek complete type inference. In particularly, we do not seek it at the cost of efficiency. Type inference must be efficient. OCaml has to type check millions and millions of lines of code, and so algorithms that rely on search or backtracking simply don't work for us. And since this is a workshop on the implementation of type systems, I'll be presenting signatures and snippets of code throughout the presentation. So you might say, aha, what you want, Alistair, is bidirectional typing, which is where you split your type checker, your infer function, into two modes. The first mode is checking, where given an environment and some form of expression and a type, you check that the expression has the given type. And you might write a function like this. And you also have inference, where given an environment and an expression, you infer the type of the expression. And this generally works by propagating types either leafward, so down children in the case of annotations, or to neighboring terms, as in the case of application. And a simple example of bidirectional typing in OCaml is static overloading, as we've seen previously in this workshop. So in OCaml, you can write two record types, for example, point and gPoint, with the fields x and y, and they're statically overloaded. And that is to say that the OCaml type checker will infer which field you meant at type checking time in comparison to dynamic overloading, where field resolution would be resolved at runtime. And so, for example, we can write the simple function getX that takes a point and projects its x component. And we're able to type check this because obviously we can see that P has the type point, and thus we can statically resolve it to a projection on the type point. And so while typing this, you might have this kind of small derivation where you infer that P has the type point. And interestingly, this is called a known type in bidirectional systems. And this means that we can robustly rely on the type information for any form of disambiguation in the case of overloading here. And this is really the secret sauce of bidirectional systems, and it allows them to express two more expressive features, such as overloading, such as GADTs, such as higher rank polymorphism. This ability to simply express when a type is considered known. But it comes at a cost, and the cost is fixed directionality. So the flow of type information can only go in a given way in bidirectional systems. It's fixed by the typing rules. So if we take applications, for instance, you would first infer the function has the arrow type tau1 to tau2, and then you check that the argument has the expected parameter type tau1, and then you infer the entire application has the type tau2. And this works in some cases. So for example, this type checks in OCaml, and that's because we're able to first infer the function and propagate the type information to the argument. But sometimes you're simply out of luck in OCaml, and you might write a function like this that doesn't annotate the parameter, but instead has the annotation on the argument, and OCaml fails to propagate the type information here, complaining that x belongs to several types, both point and gPoint. But we know, x should belong to the type point. We have an annotation on the argument, so why can't we just propagate the information in a different direction? And so the slight problem is that OCaml uses a another approach to type checking, which is constraint-based type checking. which is where we take a term, we generate some constraints, and then we solve these constraints. And the nice thing about this is that it's, well, okay, first the shield for the essence of ML type inference, which is where I found this approach from. Everyone should read it if they want to know about type inference for constraint-based typing. The nice thing about this is that it's order insensitive. We can really solve constraints in any order. And it does have many other advantages. For example, constraint generation is very easy to write, so it scales to a very large language, whereas constraint solving is rather tricky, but you can have a very small constraint language for a large source language. And elaboration is easy and modular, thanks to a paper by François Potier. So the problem at hand is that we have constraint-based typing and bidirectional typing. Both are efficient. Bidirectional typing, however, is more expressive. We're able to handle more complex features. But it has this problem of order sensitivity that constraint-based typing doesn't have. And there's been some work on improving bidirectional type inference to remove some of this order insensitivity. We first had let arguments go first, and more recently we've had contextual typing. But they still have some form of fixed directionality to them. And so our approach is omnidirectionality. So what is omnidirectionality? Well, firstly, omnidirectionality is a constraint-based approach, which means that we get the efficiency and directional insensitivity of constraint-based approach, infused with the ability to express when a type is considered known. And we express this using a suspended match constraint. This is a special kind of constraint that essentially matches on some unification variable and then will generate a new constraint based on the known type information it receives using this function f here. And so, for instance, a simple version of known type information might just be the top-level connective, for example, unit, and the fact that it's a function type. And so the key idea to solve these constraints is that if we don't have the required known type information during constraint solving, we simply wait and suspend until unification does its job, propagates the type information, and then hopefully we can resume. And that's precisely what we do. We wait on alpha to be unified. When alpha gets unified to a concrete non-variable type tau 0, we then simply solve the constraint generated by applying the shape of tau 0 to f. And if alpha is never unified, then we fail. And this kind of corresponds to when you might have a overloaded projection and you don't have enough annotations in your program, and OCaml would fail with an ambiguity error. And so the questions we might have about this approach is, how do we specify the typing rules for omnidirectionality? What properties might we expect from omnidirectional type inference? How do we even implement this? And how to do so efficiently? And how can we scale it to more complex features like let polymorphism, static overloading, hiring polymorphism, and more? And so in this talk, I'll be mainly answering the latter three questions, but you can find the answer to all of these in our paper. So let's start off with a relatively simple situation, the simply typed lambda calculus, where you have types consisting of variables, simple base types such as unit, and arrows. Now, in true Prolog fashion, we've got variables as mutable references that consist of some unresolved unification variable, null, or a link to the type that the variable was unified with. And so to implement these match constraints, the idea of waiting on a unification variable, we simply add a wait list, just like you might see in a coroutines library. And so this is actually pretty efficient in practice. And it doesn't backtrack at all. So the next challenge is how can we scale the implementation of this to let polymorphism? So in OCaml, you can have let bindings that generalize their types into more polymorphic ones. So you might write the canonical example as the identity function for next to x, and OCaml will infer this as the polymorphic type for all alpha, alpha to alpha. And so generalization is a process where we figure out which inference variables are local to the right-hand side of the let binding and can be generalized into more polymorphic ones. And so you might write something like this to do your inference code for lets. And while the code isn't that important, it does have an order, which is that we first infer the type of E1, then we generalize its type, and then we use the generalized type to type check E2. And this is a fixed order. And more precisely, omnidirectionality doesn't really play nicely with fixed orders. So this is a problem. And to see where this breaks, let us consider a more concrete example, difficult, lemon difficult, where you can have our projection function that takes some point and projects as x component, and then it's applied twice, once to Q and once to some form of G point record. And here we can see that GitX is not only applied to G points, but it also has to be polymorphic because it takes int G points and it should also take float G points. And so at the point of generalizing the type scheme for GitX, we would first note that we don't have enough type information to solve the suspended match constraint on p.getx. Secondly, we don't even know if p or the return type of GitX may be polymorphic or monomorphic at this point in constraint solving. So at the point of generalizing GitX, it could have the type point to int. And so we say such variables are guarded by p.x's suspended match constraint. And so now we have to deal with the problem of generalizing such guarded variables. And so we had a couple failed solutions to these. The first idea was, well, these are just qualified types. If we stick the suspended match constraints in the type scheme, then perhaps we can continue. This doesn't work because if you do this, you might have something like the suspended match constraint kind of looks like a has field, and you would have this in Haskell, but it results in dynamic overloading, and that doesn't work for us. We want static overloading. Can we make let bindings monomorphic like GHC does? The answer is also no, because GitX is instantiated for int points and float G points. Can we suspend all instantiations of GitX and just continue with constraint solving? The answer is also, unfortunately, no. We still get stuck. At some point, we have some residual suspended constraints, and there's no way to connect them all to solve this problem. And so the key idea we had is partial generalization, which is you don't have to generalize everything at once. You can do something slightly more incremental. And so partial generalization consists of generalizing what we know to be monomorphic or polymorphic, in this case, unguarded unification variables. And if a unification variable is guarded, then we treat it as polymorphic, and then we can patch it later if we learn that it's monomorphic. Importantly, this is not backtracking. We never revisit decisions. Types only get more precise with this approach. And to see partial generalization in action, we'll go back to our example. So at GitX, we're generalizing it, or partially generalizing it. And so we might start with the partial type scheme for alpha, beta, alpha to beta, with some residual constraint that we need to solve. And from this, we can then instantiate the partial type scheme in the body of the let. So we instantiate it twice. And then we might note at the second application of GitX that alpha needs to be unified to G point due to that annotation on here. Now, since alpha is now unified to some concrete type, we can solve its suspended match constraint, which unifies beta to gamma, and this now refines the partial type scheme to one that we expected, which is for gamma, gamma G point to gamma. And then we just patch all the instances, mapping their alphas to some gamma G point and their betas to the gamma. Now, this seems a bit complicated, so it's pretty delicate to implement, and it's incredibly difficult to implement efficiently. And I'm talking using tricks like levels and union find and mutability in your constraint solver. But luckily, we've managed to achieve this, and it's pretty pleasing. We get principal type inference. It works with ML, and we're able to express slightly more complex features that we want in OCaml without this directional sensitivity. So to summarize, omnidirectional provides expressive and efficient type inference that scales. You can check out more in our paper. We both have a declarative and principal specification for other features that omnidirectionality can be used for. We provide the details on a sound and complete constraint-based type inference algorithm. We have a formalized, efficient constraint solver as a series of rewrite relations on constraints, and the description of the efficient in-practice implementation that I've discussed in this talk. Thank you for listening.
Do we have questions?
So at the start of your talk, you mentioned bidirectional typing can do higher rank polymorphism. So can your approach do higher rank polymorphism without introducing some extra annotations?
So that's something we're actively working on, not just higher rank, but first-class polymorphism. And we believe that it is possible in omnidirectional type systems.
Without introducing like new syntax for types?
Yeah, you just add type schemes to types as normal, and so it's a normal algebra of system F types.
Okay, thanks.
How efficient is it? Can you show us the data?
We don't quite have like benchmarking data, but we have a lot of experience writing these constraint solvers for Hindley-Milner type systems, and the techniques we've used here at least inform us that we believe it to be efficient. But we can benchmark it. The problem is we don't have a huge corpus of programs that rely a lot on omnidirectionality, so the sort of bad cases for efficiency are ones that we have to craft manually.
Do you at least not slow things down that used to type check before?
Yeah, we don't slow things down at type check before. So like all the efficient techniques of levels and union find for unification that worked for ML generalization work the same for partial generalization.
Any other questions?
Thanks for the nice talk. So, is this the future of OCaml?
It maybe. It would be nice to get this in the type system, but it's a reasonable amount of work. We want to experiment more with it first before we consider including it in OCaml.
Okay, but if it works well, hopefully it will be integrated in OCaml.
Hopefully, yes.
Cool. Thanks.
I have a slightly less optimistic answer to this question than Alistair, so that it may be useful complement. When we started doing this, I was convinced that it was way too complex to consider adding to the OCaml type checker, which already has a sort of complexity problem. But then we realized that it, as Alistair, I think that the implementation is getting simpler over time of this, so that it's now only a small fraction of the overall complexity of the OCaml type checker. So it becomes reasonable to consider adding that. So yeah, we don't know yet.
There are also simpler variants that we could consider. So like if you didn't do partial generalization but added the waitlist stuff, and you'd already get improved stuff on top of OCaml. And that stuff really is simple to implement.
You said it didn't work, right?
It doesn't work, but you could have some different heuristics to deal with it that aren't as nice theoretically, but probably behave semi-okay in practice.
Thanks. Thank you for the very interesting talk, Alistair. I had the question whether, so you talk about the sort of existing systems. I don't know if you've already related them in your paper. Are you planning to show that they're more that yours is more expressive formally, or?
So in our paper, we mainly deal with stuff that, well, static overloading hasn't been formalized previously for OCaml, but we did do semi-explicit first-class polymorphism, which is a kind of first-class polymorphism used for objects and polymorphic parameters, and that is more expressive than the existing approaches, and that we can directly relate.
Thank you for the talk. Do you think this has applications in functional logic programming?
Yes, so functional logic programming has similar flavors of constraints where you kind of like do some form of if on a unification variable. It's very plausible that the semantics we came up can be applied to functional logic programming. Typically, though, the previous approaches I've seen of kind of these if constraints in FLP is that they're expressed as small step transition relations, and a large part of our work for omnidirectional type inference was kind of coming up with a big step or denotational semantics for constraints. And so you could probably reuse that in FLP.
Interesting, thank you.
Let's thank Alistair again.